The recording also. You are able to see the slides, right?
Yes, sir.
Okay, so we'll start. So last week, of course, so we have started our course, and then the Professor James said videos you have seen, and then now last week, I have we have started discussing about our things also. Okay. Now, as all of you remember, say, so what is the most important? What is the main objective of this course? Last week I explained you, right?
To identify a landing site on Mars or some other planet.
Yeah, so that is very good. So now you have to identify the landing sites. Okay. So how do we do this landing site identification? Say, so for that, geology is mandatory. Okay. So like you are sending some instruments. Say, so you should be able to locate faults. Where you will get more amount of data sets. Say, so that is how the things are. Where so the geology becomes very important. Okay. So this course is essentially about the planetary geology, geomorphology. How do we identify the landing sites? All the basic things that is very important. Okay, that's the main objective. So last week, so we have done inventory of our solar system. So like, what do you mean by our solar system, and then what are the things are there, and then finally we discussed last class how solar system forms also. Okay, like you may be having a cloud, and then things starts spinning around some this one, and slowly say, so you will have this type of disk kind of a thing. That's what they call as a protoplanetary disk or something like that. And then all these small things, say, they collide with each other, and then you see the planet gets formed. Okay. And the most important thing is, because there will be more heat, say, at the center, so all the terrestrial planets, that is, which consist of heavy metals or minerals or whatever, they get formed near the sun. And then as you go far away, so the gases and then ices, that is how our solar system gets formed. Now we have a good very understanding, basically. Okay, I also explained you the cosmogeny, like you say, what type of materials will be there very close to the sun, and then as you go far away, say, so you will have whatever type of materials also. Okay. And this is how the planet forms also, like accretion. Basically all the meteorites are the small particles, say, so they collide with one another, and then the core becomes because of the compactness, say, inside heat will come, then the core comes, and slowly mantle and other things, and finally we will have a planet, basically. Okay. So this already we discussed in our last class. So finally, so if you just see a summary, say, like whatever we discussed in the last week itself. So nowadays, so what do you mean by solar system? Solar system, now the definition is, so generally in your childhood, say, like solar system means the sun plus some planets, we used to say. Okay. But now our solar system consists of how many planets? See, how many planets are there now totally?
8 planets.
8 planets are there. Then apart from that, Pluto is not a planet, right? All of you know. So we are having 5 dwarf planets also. Okay, like Ceres, and some pro-Neptunian objects have been found out. Then I think if you count the number of moons, say, like our moon, including our natural satellite, Jupiter, Saturn, all other things, approximately some 176 moons have been discovered. Okay. Of course, this number will increase. We don't know if followed, right? Because of so many missions are going to come up in the future, so they may change also. Okay, and then almost 6 lakh asteroids have been discovered. Okay, and all these asteroids, where do these asteroids lie? Which is the region where you will find asteroids?
Between Mars and Jupiter.
Yeah, between Mars and Jupiter, you will see. And then the comets have been discussed, actually. Okay, some 3,000 or maybe more, the cometary objects have been discussed. And where do you find out these comets? See, comets are
Outside,
found
outside the orbit of Pluto.
outside the orbit of Pluto, say. So Oort cloud and others, you will find these comets kind of things itself. Okay, and of course it may increase, basically as more number of missions are there. And then we have said that among all the planets, we have said Jupiter and Saturn are gas giants, actually. And of course Uranus and Neptune all are ice giants, we have said. But the most important thing with these planets, when the spacecrafts went to these flyby missions, say, They did not observe any geological features, like you see the mountains, the valleys, river valleys, rocks, and other things have not been seen on these four planets basically. So if you want to study any geological things, say, so you can't do for Jupiter, Saturn, Uranus, and Neptune, okay? Because all of them are a gas. Jupiter and Saturn are gas giants, so you don't, we can't even land on them also, okay? And then Uranus and Neptune, so they are also gases and water vapor, in the terms of clouds or whatever, ice kind, this thing is there. So you can't land on this planet. So there are no mountains, there are no geological interesting things like volcanoes and other things, has not been observed on these four planets. So now in our planetary, this geology, are all the experts say. So Jupiter, Saturn, Uranus, and Neptune. So you can't study them geologically, okay? Because the geological features are missing. Because from remote sensing clearly shows that there is nothing, only just storms or something like that. So these four has been, geologically, you can't study these four. Apart from this, you can study many other like moon, terrestrial planets. You can study then Venus, Mars, we have put landers also, okay, like on Venus, Mars, and then Moon also. Then now Saturn's moons, Titan, and then asteroid, comets. People have sent, these spacecrafts also. And then Moon, everybody knows, right? Astronauts have gone, and the geological studies are very well known for our Moon, basically, okay, because lot of data is available for our okay. So these are very important things. So these are the dwarf planets. Okay. Of course, you may be knowing like Eris and then Pluto, say, Humia, make, So these are all pro-Neptunian objects, they say, very close to Neptune or, somewhere far away they will be there. And then Ceres, actually, this is an asteroid which lies from Mars to Jupiter. So previously there was a debate whether this is also a planet or something like that, but now it has been classified as a dwarf planet. Okay. So these are the five dwarf planets which have been discussed in our solar system. Maybe future we don't know, okay? Because the pro-Neptune objects, there are so many things, which we have not yet discovered. Maybe this number may increase or, we have no idea, okay, in future. So now we are coming to the proper the definitions actually, okay? So the August 2006 is International Astronomical Union, so that is a society IAU, okay, which gives all the definitions and authorized body kind of a thing. So they have defined what do you mean by a planet and what do you mean by a dwarf planet. You can get these things in Google also. So planet, the definition is it should orbit the sun and it has enough mass to form a spherical shape basically. Okay, so it should have a more spherical kind of a shape and it has cleared the neighborhood around its orbit basically. So its orbit, it should be gravitationally very, very strong and it should have its own orbit and it should not collide with others or it should have that much gravity. Okay, it should have cleared the neighborhood basically. And then dwarf planet means it is defined as it orbits the sun. Of course, a spherical shape is there, but it has not cleared our neighborhood around its orbit, and it is not a satellite. Like moon is a satellite, So dwarf planet means it should orbit the sun only. Okay, so this is the definition, standard definitions given for planet and the dwarf planet. And right, the Pluto, it doesn't satisfy which criteria among these three? Yeah, so which doesn't satisfy, you can see in Google, you can study also. So the third one, say the Pluto doesn't satisfy because it has some, the neighborhood, I think some pro-Neptunian objects are there, which there are some intersections, in their orbit. So they say that Pluto doesn't satisfy the third criterion and it has been made as a dwarf planet rather than a planet. Okay. And these are also some definitions, okay, that union has given, like what do you mean by a star, what do you mean by a planet, this is a different kind of a definition. So star means it should have a self-sustaining fusion basically, like our hydrogen burning, our sun kind of a thing, so it should have a fusion is there, say, so we call it as a star. And some, they have given some numbers also. Then stellar remnants, say dead star, no more fusion kind of a thing. Then brown dwarf, say. So like that, so many things are there. Okay, but of course here the definition of planet means negligible fusion actually. So there should be no fusion. Very small fusion should be there in the planet, and of course it has to orbit one or more stars like our sun or something like that. So this is another definition for planet. So like this, we have standard definitions for all the solar system objects itself. So now coming to the numbers, say now as already I showed you, like we have all the inventory we have seen in our solar system. So now you can find out all the following quantities also, like what is orbit of the planets, the mass of the planet, and then size, rotation rate, shape, and then temperature, magnetic field, surface composition, surface structure, atmospheric structures say. So these are all of this information has been available because of these flybys. Spacecrafts have gone, and from telescopic observations, people have got all these numbers itself. So now regarding the orbits of our planets, I will not go into the details because you would have studied in your physics or somewhere else, and you can get this information also. So right, the planets orbits say, so they follow, these are the famous the Kepler's laws of planetary motion. You would have studied in your, I don't know, 10th class or 11th class or whatever here. So I will not go into detail, but this is what you see the planet orbits say. So these laws are widely used to describe a planet's orbit basically. So these are the famous three Kepler's laws, like all planets move along elliptical paths, with the sun at one of the focus. And the second one, it says a line segment connecting any given planet and the sun sweeps out area at a constant rate. Right, that you have to find out the area. Okay, so that also it's a constant rate, it goes away. Then the third one, so which is very important, which is helpful in finding the mass of a planet, is the square of planet's orbital period. So that is a p square. Okay, the orbital time period of any planet. So if you square it, it is proportional to a cube, where a is the semi-major axis. That's the distance. The longest distance is from the sun to that planet. So this is a very important rule. This is Kepler derived. And then to describe a planetary orbits, they use some six elements actually. So you can see in this figure. So A is the semi-major axis. So yeah, I hope all of you know these words, right? Apoapse and periapse. Actually, apoapse is the farthest, the distance, whereas the periapse is basically the smallest one. Okay, that's how it is defined. So A is semi-major axis, B is the minor axis, and then E is eccentricity of a planet. Then these orbits, planetary orbits, are not flat. There will be some type of inclination will be there. Okay, so like you can see in this figure. So you can see the orbit of Pluto or whatever you can see, it is slightly inclined actually. Okay, of course, all the Earth and other orbits also, although they are more or less flat, but they all will show some kind of an inclination compared to the sun's this one. So so that also we define, like you see this angles F, then omega. These are all the the numbers how to define an orbit for a planet. Okay. So if you want, you can read any astronomy textbooks or celestial mechanics. So they will give you more details about this one. As far as this course is concerned, if you know just briefly, that is more or less sufficient. Okay. So these are the numbers A and E, which are orbital inclination. So these are the numbers. So you can see. So these are the orbits basically. Okay. So like you see, Earth orbit, and then the Venus and their orbits. Say. So they have plotted up to scale. So this is the inner system, inner planet, that's the terrestrial planets basically. You can see this Ceres, which is a dwarf planet, which is rotating around our sun. Then these are the orbits, say, for our, the outer planet, that is Jupiter, Uranus, Saturn, and Neptune. These are all gas giants or ice giants here. Then these are the dwarf planets. So you can see their orbits, how they are looking like. Most of them, all of them are all elliptical kind of orbits. So people have found out actually, okay, through the flyby missions or whatever. So all these numbers are available. What is the semi-major axis? What is the eccentricity? Then the inclination, the angles and whatever say. So all the information is there. So if you see Earth say, okay, but here one most important thing you have to see is the units basically. We know, right? The distance is measured in terms of AU. Okay, that I have already explained you in the starting itself. So Earth is taken as a benchmark basically. One AU means distance from the center of the sun to the center of the Earth itself. So with that, these things are measured here. And E is the eccentricity, in that one, and I is that angles, lambda, this omega, lambda, all those comes from the angles itself. So these is how we define the planetary orbits also. And this is what we call as inclination basically. Okay, so as already I told you, the inclinations say with the sun's orbit, this is also very important here. Now Earth basically has inclination of 1.6 degrees. It is not perfect zero. Some small inclinations are there. And Mercury has the highest inclinations. Okay, orbital inclination 6.3 degrees, and Uranus, Saturn say, of course, they are more or less close to zero. But if you go to this far away dwarf planets, say, you can see the inclinations are extremely high, and they don't qualify, right, because they have not cleared the neighborhood or whatever this one. So, but here the most important thing is all the planets say their orbital inclinations are very very small, which says that our solar system can be taken as a something like a flat disk kind of thing itself. So these are the numbers, and of course these are for the similarly the moons also, say like Jupiter moons, Earth moons, Mars moons also. So all these numbers have been found out. They have been estimated from telescopes. This one are some technologies are there like radar and other things they have used, or maybe the spacecraft missions or orbiters have gone, and these numbers have been calculated. Okay. Now, one more very important thing in planetary thing is this Tts Bode law, basically. Okay, so this is a very famous law. Why it works, we don't know, but it is a very kind of some kind of a empirical rule, which tells you the distance to the planets from the sun. So this law, what it says is, you take numbers starting from zero. Okay, so zero, then the next is a three, then 3 twos are 6, then 6 twos are 12, 12 twos are 24, 24 twos are 48, 48 into 2, 96, and then 192. Like that, you add these are, you generate numbers like, multiply by 2, 2, 2 kind of thing, starting from 3, and of course, 0 is also included. And then you add 4 to these numbers and then divide by 10, you will get all the planetary distances itself. Okay, so like the first one, say, so first number starts with 0. So 0 plus 4 divided by 10. That means a 0.4 basically. Then the next one says, so 3 plus 4, that is 7, 7 by 10. That is a 0.7. Okay, the next planet. Then the third one, that is 6, 6 plus 4 is a 10, 10 by 10 is 1 basically. So that comes for the Earth itself. And similar, so you can find out, so this is a very simple law which is widely used in planetary sciences, to find out, like if you are seeing any solar systems, not only in our solar system, some other galaxy or whatever, say, they use these rules to identify, where planets will be approximately located from a given star itself. Why it works in practice, nobody knows, but it works very well, very good, the approximations. Okay, so like Mercury, if you see, say, then that is 1. So that means 0 plus 4 by 10, and this is what the Tts Bode law, this predicts like is a 0.4, and if you see the exact distances, it is almost 0.387, very very close to this Tts Bode law itself. And if you see Venus, say, so this law predicts 0.7, and we have 0.723. Earth is anyway 1 1, it exactly this one. Then Mars, say, the log is 1.6, and the exact measured is 1.524. So of course, as you go far away, there are some minor deviations will be there, but this law, it works fantastic, in practice. So this law tells you if you have any stars, say, so where the planets will be located approximately. And sometimes, this law has been used, like, some planets have been discussed based on this law. So the law says at 10 AU, say, there will be a planet, say. So people used to search also at that distance, in that orbit, say, if anything is orbiting the sun or something like that also. So this law was widely used, in the olden days, or now also. I don't know why it works, but people have got some kind of an idea, like, what are the distances of the planets from the sun. Okay, very simple. You have to take starting from 0, the next number is 3, 3 twos are 6, and you double everything, you add plus 4 divided by 10, so you will get the planetary distances. Very very simple law to calculate approximately the distances of planets from the that star or whatever we have. So this is how it looks like. This Tts Bode say. So it exactly predicts, Mercury, Venus, Earth, Jupiter, Saturn, this one. But of course, when it comes to Neptune's, as already we have seen, the log is 38.8, but original thing is 30.07. But anyway, the differences are there, but it works very nicely for the planets inside our, the solar system. So these, and then these are the orbital velocities of a planet. So how much fast they are rotating here. So here also people have observed a pattern. So if the planets are very close to the orbiting stars, their velocity will be very high. And as you move far away, say, because the orbital the length also increases. As the distance increases from the sun, so its velocity also decreases. So Earth is somewhere here. So something like 30 kilometer per second is the orbital velocity of our Earth itself. Of course, as you go far away, say Neptune and Pluto, its velocities are very, very small. So this is also a pattern which has been observed in our solar system. Now, another thing is, the rotational poles, say, like if you see our Earth, it is not straight basically. So it is like a spinning tops you have seen. So its inclination, say, to the vertical is 23.5 degree, but approximately, 23 degrees, it says this one. Now Mars has inclination of, you see, the 25 degree. It has been slightly inclined. It is not perfectly straight. Then Jupiter is 3 degrees, Saturn is 1, Neptune 30, Mercury is 0.1 degree. Perfect, almost the straight kind of axis it has. But the peculiar thing is Venus actually. So Venus is 177 degrees. You can see it rotates in a different this itself. And then Uranus also, you can see the inclination is almost 98 degrees. So it spins in this direction. That's the spin axis we say. So Earth is in 23.5 or 23 degrees, you can say, for Earth. So Earth, Mars, they are very almost close to each other. So these are the spin, the angles. Okay, and these are some geophysical data. Okay, what is the mass of the planets and radius, the density, then flattening. So flattening is something like the flattening is something. So if you take any the shape of the planet basically. Okay, so like if you see this the planets, say what type of shape the planets are. Now all the planets, what type of shape they are. Spherical, but they are not exactly spherical, they are elliptical. So if you take a spherical shape, say, and then you also have this elliptical shape. So some of the planets have like this actual ellipse kind of a thing. So it is this flattening tells you it is a relation actual, how much spherical it is actual. Okay, so if it is almost one, say, that means it is a perfect sphere. Okay, so Earth, if you see, say, what is the flattening coefficient for Earth? It is 1 by 298.257. So that means the flattening is nothing but the ratio between the radius of the sphere and then its semi, the minor axis or whatever we have. So it tells you the ratio. So this flattening coefficient is almost 1, say, that means it is perfectly spherical. Okay, so if it is some other number, say, how much it deviates from a sphere, that's what they call as the flattening, this one. Okay, then semi major axis, then sidereal rotation period. Sidereal, I hope all of Earth has 24 hours. Okay, that is what they say. Then what is the solar days? In a day, Earth is 1. So it is compared with Earth. These are the solar days. And the gravities people have found out. Then equatorial gravity, core radius is how much is the inner core size. Of course, Earth we know almost because of earthquakes, but other planets. So these are all approximate estimates actually. Okay. Then oblique orbit, then sidereal orbit period. Like Earth has 1 year, okay, to rotate around the sun. How much time it takes, escape velocity, the geometric albedo. So these are very interesting parameter. It tells you the luminosity, how bright or how much light it reflects or something like that. So all these parameters have been estimated from the instruments. Okay, so these details are also available. Now this is for the giant planet. That's a gas giants and ice giants. Okay, so these are all having these masses are known, the density, radius, polar radius, volumetric mean radius, flattening also. So you can see flattening how they are, because they are not terrestrial planets. They are all like a gas kind of thing. So now all these numbers have been estimated, and then these are all widely these numbers have been estimated from the many telescopic observations as well as from the flybys. And these are also for the moons also, all the Saturn moons. So these parameters are available, and they are available in that textbook which has been circulated to all of you in the WhatsApp. Okay, so you can see if you want to know more details about this one. So these numbers are also available. Now the atmospheric composition, say, so this is also very well known. Like these are the terrestrial planets, like Earth is a nitrogen, then oxygen, carbon dioxide, methane, water, argon, carbon monoxide, ozone, and then sulfuric acid, basically. Okay, so this is also known. But the most important thing you please see here, the most important thing in Venus actually. Okay, the SO2, the sulfur, this one is extremely high actually, and this is responsible for the very high temperature for Venus also. And this is for the sun, the atmospheric composition, say. And of course sun is a star, so it will be having burning kind of thing, hydrogen and helium only. Other things also will be very very little. So Jupiter and Saturn, if you see, say, most of them, Uranus, Neptune, they will be having their atmospheric composition is hydrogen and helium only. So we don't, these things are all very very small, like water, methane, the nitrous oxide or hydrogen or sulfur. These are all very very small in those planets also. And then the surface temperatures, say, so this also has been measured by the instruments. So now the Mercury's temperature will be like this. So generally, which is the most hottest planet in our solar system? No. Which planet has a very high temperature? No, but generally our philosophy is which is more close to the sun.
Mercury.
Mercury is more close to the sun. So obviously everybody, Mercury should have the high temperature, but Venus has the highest temperature, almost 464 degrees. Because the reason for Venus is Venus has an atmosphere, and the atmosphere has a lot of carbon dioxide, I think sulfur dioxide or whatever they have. So that is the most hottest planet in our solar system. Okay, but Mercury should be the one, but Venus, because Mercury doesn't have an atmosphere, say, and Venus has an atmosphere, that makes it as the most hottest planet in the solar system. And of course, as the distance increases, obviously the temperatures drop down. And if you go to Pluto or this one, the temperatures will be minus 200 degrees centigrade, or something like that. Extremely, very low temperatures they have. Okay. And then these are the densities also, like how you want to find out in the density of a planet, so because you should know what type of planet it is. So these are some of the densities of the minerals, okay, which are widely observed in the rocks from Mars, Moon, and other things also, like ice, quartz, orthoclase. We will discuss these minerals also at a later stage, okay, when we go to the planetary geology and then geomorphology itself. And this is how the Earth's density. Okay, most of you would have seen, like Earth has very well understood. Okay, in our seismology course also we are discussing. Okay, like we have a crust, mantle, the iron liquid core, then the iron core, and of course the density of Earth, it increases with depth, and of course it goes up to, I think, maximum is 12 grams per centimeter cube, because of the high pressure at the center of the Earth itself. And then if you compute the bulk densities of the planets, so the bulk density is just mass per volume. So volume we can easily calculate. If you know the radius of the planet, say, assuming it to be a sphere, you can find out its volume. But then to calculate the mass of a planet, say, you can use this Kepler's third law. Already I showed you, right, that T square versus R cube, say. So Newton's law and then Kepler's law, that gravitation, they have given this expression, like you see, the mass of a planet, if you want to find out, say, so 4 pi square by g. G is that gravitational constant. R is the radius of the that semi-major axis, that A, whatever I showed there, and T is its orbital period, basically. So if you know these numbers, you can easily calculate the mass of a planet. So if you plot it, it is like a straight line, R u by T square. So if you know the radius of the orbit, and then the time orbital period also, if you know, so you substitute here and you can easily find out the mass. So once you know the mass, density is mass per unit volume, and volume is in a sphere kind of a thing. So you know the radius of that planet, and then you find out these ones here. So this is how the densities looks like. And the maximum density, which is a planet which has highest density among in our solar system. Yeah. So see this graph and tell me which has the highest density. Yeah. See, as already I told you, right, in the solar system, say, all the, because the sun is very hot, no? So terrestrial planets, that is a huge metals or minerals or whatever, say, they will be located very close to the solar system. As you go far away, the gases and other things, they go far away from the solar system, and then the density goes like that, okay? But here also, you will see a peculiar pattern. Which planet has the highest density? See this graph, you are able to see, right, which has the highest density.
Mercury and Earth almost.
Of course, it compares, but generally Earth is very special. Okay, so the most highest density is for Earth itself when you compare to Mercury. Okay, we don't know the why it happened. Is that we have to find out. Okay, so now this is how it goes away. So as it decreases, Jupiter's density is very low because it is all gas kind of thing itself. So you can see. So this is how the densities looks like. But of course, Jupiter, you can see the second graph. Jupiter, Saturn comes after Saturn. Say what is happening to the densities now. See, that is increasing, decreasing, decreasing, decreasing. Once you cross Saturn, say, then what has happened? Uranus and Neptune and Pluto, say. So their densities are much higher than Jupiter and Saturn, because, the temperature decreases, and ice and other, that things also gets formed in the solar system. Okay, this is how the densities, looks like. Okay, so with this, so these are some of the properties, of our solar system. Okay. Yeah. So with this, almost, we have completed our, the almost our unit one, I should say. Okay, the inventory in the solar system, we have completed, with this one. So we have discussed, to just summarize, we have discussed what are the, the inventories, what is our solar system, how it has formed, what are the most important, the terrestrial planets, gas giants, moons, and other things we have discussed. and we have known their metal properties also. Okay, little bit, this much is sufficient as far as this course is concerned. So if you want to know more about details, the orbits, all other things itself, so celestial mechanics or astronomy, so there you will see more into the orbits of the planets, retrograde motions, the mechanics and other things. You will learn in those type of courses also. But this course, as already I told you, is about planetary geology itself. Okay, so now, so with this, unit 1 is almost completed. I will share the slides in our WhatsApp group also. You can go through those slides, and of course, whatever I have presented, say, they are available in the textbooks, or if you go to any Wikipedia, or any Google websites, so they will give you, all the images and photographs, the informations are available in those websites itself. Okay. So now let us go to our unit 2, that is, as per is planetary geology and then this geomorphology. Okay. So you are able to see this slide, right? Objectives. You are able to see this slide. That is, the objectives of planetary exploration.
Yes, sir.
Yes, sir.
Okay. So now let us go to our, we are now, the object, why we have to do this planetary exploration, where geology comes into picture, and where this course fits in. Okay. So now you have studied, right, that James Head lecture, that YouTube video have already circulated, this one. So the first thing, say, what is the basic motivation for planetary exploration? Why people started this planetary exploration? What was the main reason, or what was the main motivation?
Initial history of the Earth is not known, so they started to know about.
No, that is fine. But what was the main motive? Why US and USSR, so they invested in this planetary exploration? That is that they wanted to know about Earth. What was the main background, or what was the main reason?
So they wanted to know
Not
minerals that are available in other planets.
You are seeing the slides, right?
during Cold War.
So you can see here I have highlighted also. So what was the main motivation? Not to know about Earth or not to know about anything else. Their basic motivation was politics and military, this one only. So what they were thinking was, to if you want to launch any nuclear warheads, say, so in it is very difficult to move on land or something. So these US and USSR, so what they wanted was, from space itself, you can launch missiles, and then you can destroy. So the Cold War and other things was the main motivation for this planetary exploration. You followed. So that is the main motive. That is how the funding started, and and slowly you see the objectives became very clear. Okay. So now this was the main motive. So the main motive for planetary exploration was the politics and military only, nothing else. Okay. But of course, it gave a lot of other things also. So you would have seen the first, the starting was the Sputnik actual, okay, which was launched in 1957. So this was our Sputnik, okay, which was launched by our Soviet this itself. And I think in the Professor James Head lectures, he would have shown you, right, that sound also. It just sent only, the signal, basically, beep beep kind of thing. So that was only, so this started our space age from 1957. So then once USSR started, then obviously USA also, Professor this President Kennedy, John Kennedy, he started, you see, they had a target, like, we have to, of course, politics and other issues was there, like we have to be the first or whatever to send moon on, this one. And then NASA was formed in October 1958. So this was the thing. And then, because once politics and military considerations are fine, in US, there is what they call as National Academy of Sciences. Okay, it is a group of, like in our India also, we have Indian Academy of Sciences, so which consists of all eminent scientists in the country. So they will be like a groups kind of thing. Okay, so the National Academy of Sciences was asked by the US government, to define the goals, scientific goals. Politics and military is fine, but what are the scientific goals of solar system exploration? That's the planetary exploration. So now they have defined, like many objectives, and the top three was, so they wanted to find this origin and evolution of solar system, like how the solar system has emerged, and how all the planets have come into picture, all those things. That was the most important objective. Then the second objective was life also. That's a biology, how the origin and the evolution of life has happened. This was the second objective. Then, they also wanted to know the processes that shaped our humankind's terrestrial environment. Like, you see, how Earth formed, and then how the atmosphere, you followed it, how this atmospheres, how these humans got, how we got evolved in Earth and this type of environment. So this was the third objective. Now slowly, as in the last years, say, many objectives have come. Now, what is the most important objective? Why people are doing planetary exploration nowadays? No. Of course, politics and military, if you delete, say, now what is the main objective now?
To find life in other planets.
Now, life is anyway there. Oh, this was the main objective. Now people are interested in what nowadays? Yeah. What is the main objective? Mining. You followed the mining basically. Like asteroids, I told you, right? They contain very gold minerals, very rare minerals are there. So now people have started even, the mining, and then you can earn money, followed it. All those objectives have come into picture. But these are the main objectives, which was in the starting, the main objectives you can say for the planetary exploration long back in 1960 or something. These was objectives has been framed basically. Okay. And now these are the basic planetary geology. So that is for the planetary system. Now we are coming to the planetary geology. Now what happened was, as I already told you, when the solar system exploration, the planetary exploration, the most important thing is the geology. Okay, because where to land, where we have to go, and these planets are not like small places or something. They are huge objects. So where to land, where to go, where we will get more data, where we will get more information about the planet. So that is how this geology became a very important part in our solar system exploration. So the planetary geology objectives are like this: what is the present state of the planet? Okay, not only are other planets also, like so we would like to find out, say, what is the present state of Mars. Like you see, the composition, the distribution, the ages of the rocks, whatever rocks are there on Mars or Moon or any this one. So what is the ages of this one? What type of compositions they have? They are iron or silica or whatever types of things are there. Then we have to identify the active geological processes, like for example, volcanic activity, landslides, earthquakes, quakes kind of a thing, and impact cratering. So what are the things happening on this one, the present state? And then you have to characterize interior and what lies below the planet, whether water is inside or the core is made up of iron, liquid core or solid core or whatever. So this is one of the main objective. What is the present state? So currently at Mars, is what type of rocks are there, where water is there, what are the active geological processes, and what is inside the Mars. This is one main objective, the present state. And then of course the past state also. Like for example, say, of course we want now, when it comes to the past, you would have seen that James had a lecture also. He mentioned, we also want to know our past history. And of course our Earth, because it's a very dynamic planet, so plate tectonics, atmosphere, they have destroyed all the evidences which are available to us. So this is also a fundamental aspect. So to know that also, we do this past state of other planets may give a solution to find out what is the past state of our Earth also. So this is a fundamental aspect of geology. Okay. And so the geological history becomes very, very important, like how these present states, whatever we are having, they came due to the previous conditions, or there has been some major changes or evolutions. Like in our Earth, we know, right? It was all fine, but I think dinosaurs was there. Then some impacts happened, and then this type of life came. So anything such type of major things have happened. So this is also one of the main objectives. So present state is there, then the geological history is there. That's also very important. And then other thing is the comparative planetology, we say, like how the present and past states compare with other objects. Like for example, say, like how do we compare the geological history of Earth with geological history of Mars? So whether Earth also will become like a Mars, in what way the geological aspects of these things are different from one another. So this is also extremely important objective. So these are the three fundamental objectives of planetary geology. These are the fundamental objectives for planetary exploration. So planetary exploration is different, whereas the planetary geology is it is, of course, it's a subset only, but it is different. So these are the main objectives of our geology, planetary geology. Then of course we also have one more subset is astrobiology. Okay, this is a very important thing. And of course curiosity, everybody is common people, everybody is interested, right? Are we alone, we follow, right? So like whether there is life in any in the planetary system. So this comes under the subject of astrobiology. Okay, so like it deals with all aspects of search for present, past life, research on origin of life, environments conducive for biological process. So that comes under astrobiology. And NASA has Astrobiology Institute, okay, 1998. And of course, people were working in astrobiology from long back, but this institute was formed in 1998. And this website contains all the details. If you are interested in astrobiology, you should see this NASA's website. Okay, and then initially when the planetary missions was done, so people also the Viking missions, for Mars, they were sent to search for life, basically whether life is there on Mars or not. So these landers were sent, and Viking 2, 3 missions also went, and but of course the results was all negative only. But so this was the main objective in the olden days also. So planetary geology is one aspect. Astrobiology is also another subset of our planetary explorations. So this is that Viking Lander. Okay, this image is available in Google also. So which was done to find out whether there is life exists on Mars or not, like that. Now in astrobiology also, they have now initially they used to do something like a random, but now they also have very clear objectives. Astrobiology. So the main object, and of course this also links to geology also. That is, they say that presence of water. So if you want to have life, water is very important. The presence of water and essentially liquid state only. So the astrobiology, so they also want to know these details, whether water is available in a liquid state also. Then of course the second objective is a sufficient energy to support biological processes, and of course this organic chemistry and carbon, nitrogen, hydrogen, oxygen, phosphorus, and sulfur. So now whenever the spacecraft is being sent to say, they will have instruments, okay, which can to detect water and then to detect carbon, nitrogen, hydrogen, all these elements also. So now astrobiology things now, right now the mostly right now the Mercury, Venus is this one. So now people have narrowed down to Mars, and then Jupiter's moon Europa, and then Saturn's moons Enceladus and Titan. So people say that there may be a chances of astrobiology, and then now I think probes are being sent to these planets also. Okay, and of course Ganymede. One more thing is that maybe the potential is in the past there was a life, so this astrobiological things also have been carried out. And then I just wanted to say here, like you see, there's astrobiology. This got very much interested in 1996. Okay, so 1996 there was one meteorite. Its name is ALH 84001. So this is that meteorite. It was discovered in Antarctica. Okay, so what they found out was, they found out that this meteorite has been come from Mars. So in the Mars, when there was a bombardment, bombardment some million years ago or something. So one piece entered our Earth and then it crashed maybe in Antarctica. So what they said was, so this mainly created a lot of interest in astrobiology. Initially, they found out that this has, some fossils or life was there, and then that is how this astrobiology subject started. Okay, but of course now they found out that it was negative thing only. But then this gives a very important. Suppose if you do some astrobiological research and if you say that if you are getting a negative result, like there is no chance of life, so you can ask, like you see, the present or past environments are found that are amenable for life, but life is not found, say. So then one must, you can ask this question: what is the speciality about our Earth that makes our planet unique, say, for life? So these questions are also can be answered. So this astrobiology field also, has almost moved forward also, like our planetary geology, and both of them are something like interlinked kind of thing, because water, lakes, and other things, geology also we study the formation of lakes, formation of basins, and others also. So astrobiology is also slightly linked to our planetary geology also. And another thing is, recently you would have seen, like Mariana Trench, many places also people have found extreme conditions, temperature, pressure, biology is there, below the oceans also there is a lot of life is there. So then that also has made people, that life can evolve in extreme cases also. They are searching for this, life in our solar system also. So this is that as meteorite, okay, Mars meteorite. It is, I think, some museum they would have put it also. So now how do we, what is the strategy say? So if you want to do this, the planetary exploration, so what is the strategy or what is the methodology, how people does this one? Okay, so now what they do is like this, basically. So the first thing, say, if you want to let us say study about Mars, we have so many things in our solar system. If you want to study our Mars, say, what is the first step people do now? So they do this telescopic observations. Okay, this is the easiest thing from our Earth. There are huge telescopes are there. So with those telescopic observations, So they try to find out, the fundamental characteristics like mass, radius, how much luminosity. I showed you, right, in the previous slide, all those details, the orbits and other things. So this is the first step, the telescopic observations, and of course our Hubble telescopes and other things are there. So they do all these observations. This is the first thing. Now, once this has been done and we get some kind of, an idea, say, like, some kind of this one, the next thing what we call as a flybys, they say. So flyby means, we just send a spacecraft. It just passes via that planet itself, like our Voyager, So I already mentioned you, right, like Voyager 1 and 2, they were basically flyby missions. They did not go and rotate around Jupiter, or they are not orbiters. So they just passed our solar system. So while going out of the solar system, so they just passed very close to Jupiter, very close to Saturn, moons and others. So they have taken pictures and they have sent back actually. So this is what they call as flybys. So this Voyager 1 and Voyager 2 are the flybys, they just went, they did not took photographs and then they gave some information about our planet. So this is the second step. So the first step is telescopic observations, and the second step is basically the flybys actually. So we collect some data, some kind of images, and because this spacecraft will be passing that planet side, it will give some photographs, images and others. Only some hours or few days it will be there. So that information is used, and then they study this in a very rigorous fashion. And this data is much better than Earth-based telescopes because the flyby is going very close to the planet. So it gives you more information. So Voyager 1 and 2 was the main objective was they are all flybys, to get these planetary systems. Now, once the flybys are done, now next is we use the orbiters basically. So what they do is, they launch a spacecraft. So it just goes and it just rotates like our moon is rotating to our Earth. So they rotate around the full planet itself. So while they are doing this rotation, and they will be the orbiters will be there for years also, like our Chandrayaan 1, it was sent as a orbiter for moon. Even Chandrayaan 2 also orbiter success, but I think the lander collapsed or whatever. So these orbiters, so they will be doing and they will be measure, the topography data, that radar mission they will use, the topography, the magnetic field, other details. So they will orbit that planet and they will give you photographs and then topography data. All those informations will be done through this orbiters. Now, once they do this polar near geophysical data, topography, they comes from the orbiters only. So like for lunar, the moon, there is, I think, a Grail mission, or I don't know, some lunar orbital camera was launched. So that took all the images, the topography through the radars, they have found out the complete topographical data is available for moon and Mars. Venus also, they plan these orbiters. Now the orbiters, the advantage is they collect all the global data. Now once you have all the global data, now next comes, the landers basically, that is the rovers. So what they do is from these images, now the challenge is you have to identify the landing site where you have to land the rover such that, you can get the more data and then you can verify the ground truths or something else, all kinds of things are there. So that is the next one, that is the landers come. So first thing is a telescopic observation, then comes the flybys, then comes the orbiters, then comes this rovers itself. So now landed missions, nowadays, when if you have landed, but you want mobility also, like these rovers, they put wheels so that they can travel up to distances, take images, may take some samples also. That is what the rovers is. Now we have seen that recently NASA has sent a helicopter also. It's a Mars copter, they say, to Mars, where it can fly and then up to large distances, and it can take close photographs and then and then it can send to back to Earth itself. So that is a landed mission. So now but the advantage of landers means they can land there and you can get data directly from the planetary surfaces, and they can even drill cores and other things also. But of course the landers, the most important disadvantage is as I already told you, these planets are so huge actually. So you go to one point, you land only at a point, and then you get all the data set. That data cannot be used to generalize the complete planet itself. If you compare our Earth, like Earth has geologically huge variations are there. So if you land near Hawaii or something, that is a volcanic activity. So then you cannot say that whole Earth consists of volcanoes or whatever. The geological things are entirely different itself. So this is one limitation with these landers also. So these are the Mars Global Surveyor, So you can see in online also, which is rotating the Mars Express. So many orbiters have gone. So these orbiter objective is they will be rotating around the planet and generating the topography data, magnetic field, geophysical, all the data will be estimated from this orbit. This is one. the recent Chengi, that is the China's thing, where they have launched it to moon. It is orbiting, and it has a rover also. It has landed on the far side of the moon, and it has collected the data and then came back to Earth also. Okay, so this is what they call as orbiters. And now sometimes what they do with this orbiter, these landers is, so they land it and then they take the samples and then they come back also. Sometimes samples are also returned through the rockets or whatever here. So once the advantage is, once you get samples from there, say, then if they bring back to Earth, we have a lot of advantages. You can test it in our own labs, and then we can find out ages and other things also. So this is also one aspect actually. Then, but the best thing is, compared to flybys, compared to orbiters, compared to rovers and other things, the best thing or the easiest thing if you want to know about a planet is you have to send humans itself. The main advantage of humans is, we are not like robots. We have the ability, right? We are all intelligent beings or whatever, so we can analyze and synthesize data quickly. We can make decisions on the spot, and then we can easily respond the results itself. So no machine can match the human attributes. But the most important thing, what's the main negative thing about sending humans? Yeah, what's the negative thing for sending humans into space or to other planets? Yeah, what's the main? Yeah. It is risky also, and it is extremely
Expensive.
yeah, it is expensive. I don't know how many of if you want to send a human being to Mars, say, and then let us say you have another mission sending a robotic mission to Mars, almost for one mission of sending human beings, you can send, I think, 100 rovers to Mars. You followed. So 100 missions to Mars, 100 rovers you can send it to Mars is equivalent to one, you are sending a human being. You followed. So that's very, very expensive, 100 times expensive basically for sending humans to other planets. That's why people do a lot of study, and then only that's why Apollo program, people are not, they abandoned, because it's extremely expensive kind of a thing. So for sending one human being, you can send 100 robots to the planets to get more data set itself. And of course, in all our I think the only, apart from all the planets, all the objects in our solar system, only moon we have been able to send astronauts, and then a lot of data sets have been came from moon itself. So this is advantage of sending, so this is a rover, okay, which was sent it to the Mars itself, and this is Apollo. So what is the advantage of human beings, when they send it to Apollo program, say, so they have put instruments, geophysical instruments, seismographs they have done. They have even done a MESW test, a passive testing, active testing of this itself, and they have recorded also the data. So these Apollo 12, the data for some earthquake, this has been they have recorded also all the data sets for moonquakes, say, they have recorded. So this information came back because humans went there and they instrumented them, and then they brought back this data set itself. So these are the some number of studies actually, okay, like for moon, say, till date, okay, so like 6 flyby missions have gone, and of course this number will increase in future. So 27 orbiters have been sent to moon to get all the data, and 11 impactors. They also used the impact, some satellite, they just the orbiter itself, they purposefully impacted the moon to know when the impact is there, say, so they can find out what is inside the moon. So that also they have tried, and the 9 landers have done. Okay, of course our Chandrayaan 3 is going this year, so they are also sending a lander. Okay, the seismic instrument is also going on the moon itself. Then there are 3 rovers have gone to moon, and then 8 samples have been returned. So some rovers, they went there and then they collected the data and then came back to Earth itself. And of course there were 6 human missions was also there on moon also. Now if we compare other planets, you say no human missions have gone, but these orbiters, impactors, rovers are you follow, right? The next comes Mars, and then now slowly say flybys. So Venus have gone, Mercury has gone. Then in the outer solar system objects, say, like the we have sent these Voyagers, Cassini, and others also. Then the scattered these smaller solar system bodies also, like comets, asteroids also. Many people have sent, and then they have brought even the samples also from these systems also. Okay. Now once in our so in our planetary explorations, once what people does is once a mission has been done, like the InSight mission or whatever, so what they do, this NASA or whatever they do is all the results actually they publish in they present in these conferences. So people wants to know, so there is a one lunar and planetary science conference, which is held every time March in Houston. Okay. So they publish all these results. Then American Geophysical Union conferences, planetary science, EGUs, Euro Planet, Geological Society of America, Meteorological Society of America. So these results will be presented in these meetings also, and then they will be published in Science News, Space News, Planetary Reports. All the data will be reported once a mission has, successfully done so. So they report all these things. And then generally, whenever a mission has gone, say, the first papers will come in Science Journal or Nature Journal. Special issues, like you can go to the website in Science or Nature. There has been a special issues on InSight mission, where which has, I think, 2-3 years back it went to Mars. So all the details will be reported in these journals, basically, very quickly within the 6 or 7 months from the mission. It's after the successful landing of your rover or whatever. Then after that, once then full papers, so planetary missions, they do a lot of rigorous review and others. So they will publish mostly in these journals. I showed you already the Journal of Geophysical Research, Planets. So the journal is a very famous journal. Very detailed analysis will be reported in this journal. Then there is one more journal, ICARS. Okay, this also it comes from Elsevier. So there also these details will be presented. Then Earth Planetary Science Letters, Planetary Space Science. Then there are some more journals like Space Science Reviews or whatever. So in these journals, they will do a detailed studies will be put up in these papers. Initial results will be published in Science and Nature, and this is how we get to know from these results. And then they will release the data to public, and anybody can download from those websites, and then we can do all our analysis also. Okay, so this is how the planetary exploration goes away. So anyway, I will stop here. We will continue in our next class. Okay. So if you have any doubts, you can ask.